Let's look at some examples of arithmetic series. So the first thing I would sort of have at hand is these formulae, the sums of an arithmetic series. But you can decide which one you use. One will quite possibly sort of lend itself to the question more than another. We've also got the nth term, remember, so that's one to learn, but that's just there alongside as well. We'll probably still end up using that in different places. Okay, so this first question, find a formula for the nth term and the sum of the n terms for this arithmetic sequence. We've dealt with the nth term previously, that's un, but now we're being asked about the sum of n terms, that's this capital Sn. So let's deal with it. We've got the first term is 1. We've got the difference, the common difference is 3. It's clearly going up by 3 every time. So if I want the un, then I can just substitute in, just as before, 1 plus n minus 1 times 3. I can straight away put the 3 there instead of having times 3. It's just more algebraically better, I suppose. And then I can simplify this. 1 plus 3n minus 3, which equals 3n minus 2. And we're done just as before. But what about Sn? Well, it's the same kind of thing, but now I'm going to use this formula that we've derived. It's going to be a half n, and then 2 lots of a is going to be 2 plus n minus 1 times 3, so I can again put the 3 there. Now, best to simplify this, I think, a little bit. It's going to be a half n 2 plus 3n minus 3, so it's a half n 3n minus 1, and I'm happy with it like that. It's a factorized quadratic. Note that when you add the terms of a linear sequence, you get a quadratic. I mean, that's what this formula is. It's a quadratic, and you can sort of see if you write a few terms of the sums down. The first term would be 1. The second term of the sum would be the sum of the first 2 terms. It would be 5, and then it would be 12. And you can see if you look at the common difference and you actually reconstruct the linear sequence. The first difference is a linear sequence. The second difference is then a constant. So that's just linking back into previous topics. Actually, we don't need to find the nth term of quadratic sequences on this course, but I'm just throwing it in to link back to that topic. But in our case, we've got a formula, we know how to use it, and that's it. All right, second question. What if we're given part of a sequence and we're told the sum? So recognize that it's an arithmetic series. Actually, that should have been series in the question, technically. A is equal to 20. D is again equal to 3. This time, I've got the sum of the first n terms. I'm going to call it capital N to mean like a particular amount, not just little n, which can vary. So that is going to equal, I can just hop up to it. I'm going to use this formula here because I don't know my last term. And it's going to be half capital N, 2 times A is 40, just remember to double it, plus capital N minus 1 times 3, bring that 3 there, and we know that's equal to 680, we're told it. So we just have to solve this equation now. I would multiply through by 2. Then simplify this, n 40 plus 3n minus 3 equals 1360, n 37 plus 3n just normal way of dealing with this sort of equation. Expand it out, turn it into a quadratic. So if I expand this, I'm going to get 3n squared, add that with that one and that one, plus 37n minus 1360 equals 0. This is going to factorize because n is going to be a whole number when we're interested in it, but it might not factorize very easily. I mean, it's got to be 3n and n here. But there's a lot of possibilities for 1360 finding the factors. although they're going to be like not too far apart. Although you've got this sort of, this 3 and this 1. Okay, let's not worry about that. Let's deal with the quadratic formula. You've got a way of doing that directly on your calculator. I'm going to have to just put it in full. So actually, I will write it down first. It's going to be that n is equal to minus 37 plus or minus 37 squared minus 4 times 3 times minus 1360. Sorry, I'm running out of space here. This is the shocking bit of working. Yeah, I can put that in. Fraction minus 37. Now, I'm actually only going to be interested in the positive solution. I'm not interested in a negative value of n. That's going to be redundant for this question. So it's going to be plus the square root of 37 squared minus 4 times 3 times minus 1360 divided by 6, which is twice a, and I get 16. Ignore negative solution. Brilliant. There we go. That's the number of terms. To find the last term, well, I could sort of resolve this equation to find L, but probably best at this point to just use the nth term. So U16 is going to be A, which is 20, plus n minus 1, which is 15, times the difference. So I'm going to get 65 as my answer for the last term. Sorted. Quadratics popping into our lives once more. All right, last question. This is a wordy question, applying sequences to it and giving some sort of context to it. Prospectors are drilling for oil. That means they like looking for oil, essentially. The cost of drilling to a depth of 50 meters is £500. Drill a further 50 meters costs £640, and hence the total cost of drilling to a depth of 100 meters is 1140. Each subsequent depth of 50 meters costs 140 more to drill than the previous 50 meters. Show that the cost of drilling to a depth of 500 meters is £11,300. Well, let's get some numbers down to get our heads around this. So if I want to drill to just 50 meters, then it costs me £500. If I want to drill to 100 meters, then it's that 500 plus another 140. So I'm going to be adding on 640 in total, because I have to add these together. So this is the next 50 meters. Really important to set this out. I think this question can be quite confusing when you first see it. And if I want to do the next 60 meters, then each subsequent extra depth costs £140 more to drill. So this is going to be 780. But so to do 150 meters, I'm going to have to add all of these together, and so on. And what I'm interested in is if I want to drill to a depth of 500 meters, how much would it be? Well, this is 50, this is 100, this is 150, then it'll be 200. Well, the number of terms is going to be 500 divided by 50, which is 10. So I'm interested in the 10th term. Therefore, I've got the n is 10. I've got the a is 500. I've got the d common difference is actually 140. So S10 is going to equal, let's just bring back our formula from before. It's going to be a half times 10 times 1000 plus 9 times 140. So that first bit's just 5 times bracket 1000 plus 9 times 140, and we get 11,300. It's always nice when you get the answer they've asked you to get. Okay, here we go. I think the main difficult bit of this question is setting it up. It's like realizing exactly what's being asked for, realizing it's a sum. This is an arithmetic series question. We're adding these up. This is how much it is for 150 meters. You actually have to add those together and so forth. Right, the total sum of money. This is going to be very similar now to the question I've just done. The total sum of money is 76,000. Find the nearest 50 meters, the greatest depth that can be drilled. So now we need to deal with the problem in reverse. I'm going to delete this just so I've got some space. Okay, I'll keep that. Right, so now I know that I've got 76,000, and that's going to equal a half times n. That's like the number of 50 meters essentially, because the first 50 meters was when n is 1, the second 50 meters was when n is 2. So n equals number of 50 meters. Just going to remind myself of that. Then I'm going to times by 1,000 again, plus n minus 1 times 140. And we got ourselves another quadratic to solve. This does not look particularly nice. I think I'm going to, this time, instead of timesing this by 2, I think I'm going to multiply through by a half, because that's going to work out all right. So it's going to be 500n plus plus 70n n minus 1, because I've just halved 140 and then I brought that to the front along with that n. And that's going to then be 500n plus 70n squared minus 70n. So 70n squared, we've turned it into something we can deal with now, plus 430n minus 76,000 is going to equal 0. Makes sense to just divide through by 10. It's okay because it's an equation, we can do that. They're all gone, but it's still not particularly nice. Will this factorize? Actually, because it says find the nearest 50 meters, that kind of tells me it's probably not going to factorize. In any case, I'm not going to try here. I'm just going to work it out using the quadratic formula. N is going to be minus 43 plus or minus 43 squared minus 4 times 7 times minus 7,600 square rooted divided by 14. Again, ignore the negative because that's not going to be a physical solution. Okay, I've got a double negative, so I can just ignore that and do 4 times 7 times 7,600. Whoops. And we get 30.0215. Ignore, I should probably just say ignore a negative solution. Right, that means with my £76,000, I can just go just over 30 lots of 50 meters. But to the nearest 50 meter, it's going to be 30. So 30 times 50 is going to be 1,500 meters. Because remember, this was a number of 50 meters. So that is my answer. Not this, just a little bit trickier, this kind of question, because we have to figure out what is really being asked and get it into numbers. Once you've done that, then essentially, if you're finding the sum of terms, you're just substituting into a quadratic expression. If you're given the sum of terms, then you have to solve a quadratic. But those are the two main kind of types. There are other things you might have to do with sequences, but I think that's, we've covered the main stuff. We've shown where the formula comes from, which I think is the neatest bit of the lesson, to be honest, and then it's a case of applying it to different situations. Welcome. Today we're going to look at the sum of an arithmetic series. We've talked about what an arithmetic sequence is. It's simply a sequence that goes up by the same amount every time, 2 in this case. Sometimes it's called an arithmetic progression. You might see that word, so just be aware. We know that sometimes it's also called a linear sequence. It could be a linear progression even. So what is a series? Well, the sum bit gives it away. A series is simply when you start adding up the sequence. You start with the first term, and the sum is then the result of what you get if you happen to add those up. So the example of an arithmetic series that we've got here is 5 plus 7 plus 9 plus 11. And if we were to add that up, we could figure it out. Be 20 here, add 12, 32. Question is, how can we do so more quickly? What if I had a million terms? What if I just knew the starting term, which we've called A, and the common difference, which we've called D? Is there a way of doing it quickly? And the answer is yes. First of all, here's a little history lesson on this. So Carl Friedrich Gauss was around in the 1800s, and he's recognized as being one of the greatest mathematicians of all time. He's up there in my top 4. My top 4 are Archimedes, Isaac Newton, and Leonard Euler, and Gauss is in there as well. This is arguably, you can disagree, but they're definitely up there somewhere. And during his lifetime, he made significant contributions to almost every area of mathematics there was. He also worked on physics, astronomy, and statistics, and you will see some more of his what he came up with. I mean, it will already be in there what you've been covering, but there will be some more in the stats and so on. You might want to investigate some sorts of things he came up with. Anyway, one story of his talent is when he was young, his class was asked by the teacher just to keep them occupied to add the numbers from 1 to 100. So off they went, some of them like just adding them one at a time. 1 plus 2 is 3, add 3, we get 6, and so on. However, Gauss managed to do it really quickly, and he simply walked up with his chalkboard and he'd written down the correct answer, 5050. Teacher was amazed, but Gauss explained how he did it, and this is how he did it. So this is an example of an arithmetic series, and we are finding the sum. So what Gauss did is he wrote the same sum down, and I'm going to call it S again, but now he wrote it in reverse. So it's going to be 100 plus 99 plus 98 plus ... all the way to 3 plus 2 plus 1. And if you look at this, you can see that I've got pairs that add to 101. All of them add to 101. Now I can imagine adding these two things together. So I'd have 2s, which is 101, plus 101, plus 101, etc. How many pairs do I have? Well, I had 100 number to start with, so I'm going to have 100 pairs. And therefore, 2s is going to equal 101 times 100. Or I could see it that I've actually, because I've doubled the sum, I've essentially got 50 pairs overall. In any case, I can write down overall that s is going to be 101 times 50, because I've divided this one by 2. And we can quickly work that out. That's going to be 5050. So that is how Gauss was able to do it really quickly, and such a lovely method. All right, what I want you to do is to repeat Gauss's trick. If you already have seen the formula before, you're not allowed to use it here. I want you to try and obtain the formula. That's the route we're going. So pause the video and have a go at seeing if you can work out the sum of these arithmetic series. They're slightly different. They're not going up by 1 every time, but it's the same kind of idea. Have a go now. Right, so if I repeat this trick here, well here I'm going from 2 to 100. That's essentially, I've just got rid of all the odd numbers, so there's going to be 50 terms. And then if I write the same sequence down, it's going to be 100 plus 98, etc. And this time I can see that the pairs are going to add to 102. So I've got 50 pairs that add to 102, except I've doubled the number of pairs. That's my 2s. So s is going to be 50 times 102 divided by 2. Might be best to work out the 50 times 102 first, because I can just times through by 5, which is going to be 510, and then times through by the 10. Still need to divide by 2, and I think I'm going to get 2,550. Okay, let's do the same again for this one. So this time, if I had 1 to 1,000, I'd have 1,000 terms. I'm going to have, I've got rid of all the odd ones, so I'm going to have 500 terms. Again, write it in reverse, and I can see that this time my pairs are going to add to 1,002. So if I add them together, I'm going to have 500 lots of 1,002. We're going to get nearly the same sort of idea, the same sort of thing. If I times by 5, I'm going to get 5,010. But now, whoops. But then I'm going to need to times by 100 again, so it's going to become this. And finally, if I divide through by 2, probably might want to be getting a calculator out for this. I think it's going to be 250,500. So that's my answer. Oh, I mean, it's taken a bit of time, but we can do it. And then the last one, now it's going up in 5s. So it might be a bit trickier to work out the number of terms. I think because I'm basically adding on 5 20 times, then I've got 20 lots of this common difference. I'm going to get 21 terms in total. If I'm not too sure, then I can use my formula from last time, the fact that the nth term is equal to a plus n minus 1d. This is my last term. So a is equal to 2, d is equal to 5. So 102 is going to equal 2 plus 5, capital N minus 1. That means 100 is going to equal 5 n minus 1. Divide through by 5 to give 20, add 1, yes, I'm going to get 21 terms. Okay, I've checked that out. Now I'm going to do exactly the same again. I'm going to write it in reverse, 102, then 97, all the way down to 2. What's it going to add up to? I can see it's going to add up to 104. So if I add them again, it's going to be 2s is equal to 21 lots of 102. Remember, I've double counted. So I just need to figure this out now. 21 times 102. Okay, I might get my calculator out at this point. 21 times 102 divided by 2, s is 1,071. Okay, main question now. What if we make it more general? We don't have a difference of 2 or 5. We don't necessarily have a starting number of 2. We go for this. Can you try and find the sum of a general arithmetic series? Right, how did you get on? Well, we know that because we know this is the nth term of an arithmetic series, we know that there are n terms now. So that's a pretty good start. I'm going to write down, just as I did before, I'm going to write it in reverse. A plus n minus 1d plus a plus n minus 2d plus a plus n minus 3d, etc. And then when I get to here, it's going to be plus dot dot dot, and then this is going to be a plus 2d plus a plus d plus a. And now what happens if I sort of look at each pair? Then it's like I've got okay, I can see that each pair is going to be A plus A plus n minus 1D. If you're not convinced, let's look at the second one. The second one is A plus D plus A plus n minus 2D. But this extra D is going to mean that if I factorize that in, this and this are exactly the same. So it is the case, you can expand it out if you want to try it. If I add them together, if I add both of these sequences together, just like before, I'm going to get 2s. And how many terms have I got? I've got n pairs, because we said there were n terms, n pairs of this A plus A plus n minus 1D. I'm nearly there. That's going to become n, I'm just going to put a bracket in there now, 2A plus n minus 1D. And so finally the answer is S equals a half n 2A plus n minus 1D. And we have obtained how to sum any arithmetic series. And we could go back to these earlier ones now. We could let A equal to 2 and D equal to 5 and n equal to 21. We'd have to know the number of terms. And we could simply use this formula, a much quicker way which we can use from now on. But the point is we've obtained it in the same kind of way to how Gauss obtained it for his first series. So if this is just a little summary. We've got the nth term, which you need to know. This is given in the formula book. I've just derived this. We typically call it capital S and then a little n. The n means how many terms we're summing. So if I want to sum 8 terms, it would be S8. If I want to sum the first 50 terms, it would be S50. That's what that little n means. Note, the nth term is A plus n minus 1D. So if I'm summing these terms, I can say that it's the first term, A, and then as I did before, I wrote A plus n minus 1D. But if I'm summing my n terms, then this is going to be the last term. So that's what that L means there. There's two different ways of writing this formula. And if you knew the first term and the last term, then you could simply throw it into here a bit quicker. But this one will always work as well if you figured out if you know some of this information. So just be aware of both. One might be advantageous over the other in some cases.